So let's start today's lecture. So it is lecture number 7. So today we basically see the goodness of a feed. Now in the previous lecture we have learned the um, when parametric, non-parametric, how to estimate non-parametric distribution, or you can say that when we lose the assumption that our observational random variables are coming from a particular distributions, then how one can deal with that data. Now today we will see the goodness of the fit. So let's see goodness of the fit. Today we will basically learn the goodness of fit problem. So what does it mean? So sometimes experimentalists from the observation, from their prior observation or from the observed data, they can guess that these data are coming from some particular class of distribution, but from the data it is not possible to estimate some parameters. So in these cases we will check whether or not that particular data is coming from distribution or not. So sometimes experimental has a suspicion or prior belief that the distribution belongs to a particular parametric family. Now how can you check that these suspicions, or you can say the prior belief, how your prior belief or suspicion is actually fitting with your data, observational data. So how good your suspicion is, so to check that we use the goodness of the fit problem. So one of the method is chi-square method that we will learn here. Chi-square method. Chi-square goodness of fit test of Carl Pearson that we will learn here. So suppose there so chi-square, these will learn. So there can be two possible cases. One of the cases is that we know the distribution, the experimenter know the distribution completely, that means, and other cases see know that the experimenter knows the parametric family, but he does not know the parameters of that distribution. So there can be two possible cases. One is that so chi-square, goodness of the fit test, uh, the random, suppose the random n samples are, or the results of n identical experiments is that x1, x2, now xn. The idea is here, the idea is to see whether they occur according to a given probability distribution, probability density function. Suppose that probability distribution, this is density function, so this is PDF, this is not PDF, this is cumulative density function, cumulative distribution function, so this is CDF. Now the ideal situation is we completely specify the F0x, but often what happens, often it happens that one might, often we only point out the particular family without being able to specify the parameters. So we'll see these two cases one by one. So let's first see the cases, the case with it if we know completely the function we know, or completely specified distribution function, completely here. So here our hypothesis is we set up the following null hypothesis for testing. So H0 is fx that my that in the previous lecture we have seen the empirical distribution function. So here our null hypothesis is based on these observed data. If one can write a one can always write a empirical distribution function, and our null hypothesis is here that our empirical distribution is equal to that our guess or that our suspicion that this distribution for all x. Now you see, we will check how good our null hypothesis is or when we can reject our null hypothesis. An alternative against alternative h1, that is our empirical distribution function is not equal to f0 x. So that we will check. So how we will do so? So this is the thing. Now how we will do so? Let's see how we will do so. Now suppose that we suppose that our observe we can ordinarily sorted the or randomly observed distribution, the randomly observed variables. That means suppose that we observe okay, suppose that we observe, suppose capital M number of observations. We observe M number of events. So that is we have M random variables. Now if I can ordinarily assort this M random number into k groups, so it's look like that my first number is a0, which is less than a1, which is, sorry, let me write it x, that will be clear. So my random realization of these M random variables are that suppose x0 is less than x1 is less than x2 is less than xm. Now these are my observations that I ordinarily assort my M observations. Now if I can now let minus infinity, suppose this is suppose there is minus infinity, or you can say like that, that is minus infinity comma x0 then from okay, sorry, this is not minus infinity, you can write it like that. Suppose x0 x0 to x1, then x1 to x2, and a k minus 1 to xm, so these I partition this observed value into k group, 1 2 3 k groups, into k groups. So the p partition of the real partition the observed values into k intervals. Okay, so first of all I partitioned into k intervals my observable after random after ordinary assorted them after or after the if I arrange ordinally, after that I make a I do a partition of k groups. This is my observation. Now suppose from and since here since so x0x is completely known, so under the hypothesis, since under the if I assume that my hypothesis is true, then I can exactly calculate what is the probability that random variable will be in the range between x0 to x1 and x1 to x2 and xk minus 1 to xm. So completely known we can find the probabilities given by 8 for the intervals, for the k intervals mentioned above. So that's it. Under if my null hypothesis is true or under the hypothesis, we can completely specify the probabilities. What are the probabilities that my observation will be lie between x0 to x1, x1 to x2, so that I can completely specify. Now you see there are two things. One is my hypothesis, one is my suspicion, one is my prior belief. This is my hypothesis. Another thing is my observation. So this is my observations. And suppose these probabilities, suppose these probabilities are denoted by pi, p1, p2, the probability of being in the first interval is p1, in the second interval is p2, so in the kth interval is pk, and summation of pi's I equal to 1 to k should be 1. So these are my hypotheses, these parts are hypothesis. Now in the observations, what we observe, that in between x0 to x1 there are suppose oy number of suppose, or let oy be the observed number numbers be the observed number of observations in the ith interval, then these should be m, since there are m intervals. So suppose it is not m, suppose I have observed n, so I equal to 1 to k, I observe n observations, so this should be m. Now the probability of the observation in the ith interval is pi, hence the expected, what is the number of expected observation? Expected observations in the ith interval, that should be n into pi. And this suggested that we should look at the discrepancy between the observed value and the expected number, that should give us, since this is the expectation of this is the number of observation that one expect from the ith interval, and one actually observe y number. So if these pi's are the true distributions from where my observation comes, then this discrepancy between oy and pi should be, if it is minimum, discrepancy should not be there. So that's why one should check for the goodness of my hypothesis or goodness of my fit, that if I fit my data with a distribution f0x, then how good is my theta, that will be determined by the discrepancy between this y, the actual observed number in the ith interval, and the expected observation in that interval. So that is chi-square I equal to 1 to k y minus npi its square by n pi. And you see that why and this will follow a chi-square distribution with k minus 1 degrees of freedom. This will follow k minus 1 degrees of freedom. That's it. Now when one will reject So why it is k minus why it is chi-square distribution, that one can see from here. Suppose that this is some interval, and the probability of occurring a single observation is, if I observe one time, then the probability of occurring single event is pi. That means it could be thought of like a Poisson distribution, and what will be the mean value of that Poisson observation, that will be npi, and that means if I observed y, so their mean is npi and the mean is pi. Okay, let me write it. So this is suppose a interval, so this interval is suppose this, and the probability of occurring a single event is pi, and if I observe n times, what will be the mean number of observation here, that will be npi, and this looks like a Poisson distribution. From the definition of the Poisson distribution, we know that if the looks like a Poisson distribution, and the Poisson distribution means e to the power minus lambda to the power n by n factorial, where the lambda will be, so this should be k, this should be, I think, okay, let me not use it k, suppose L, and this is L, suppose this is O, okay, L, this is L factorial. And what does this L means? How many times I observe that event in the region. So let me so this is a Poisson like distribution, Poisson distribution. So a Poisson distribution, then mean of that Poisson distribution is npi, and what is the standard deviation, that also npi. Now you see, we know that if this is the case, from the from the central limit theorem, we can prove that we can prove that if n tends to infinity, then this will follow a chi-square with k minus 1 degrees of freedom. That's it. Now this is the thing. Now what is our test will be? The test will be, as large deviation between observed and the expected value provide the evidence against the null hypothesis so then we reject it if the observed value is greater than alpha percentage, upper alpha percentage value of the chi-square distribution with k minus 1 degrees of freedom. So we will reject the hypothesis if our chi-square is greater than chi-square k minus 1 alpha. So if this happens, we will say that our hypothesis is not good, our fit is not good. So that's how we will check our fitness, check not fitness, check the how good our suspicion is, or how good our null hypothesis is, or how good our prior belief is. Now let's see some example, that's where it will be clear. And another thing, another thing is, so this is when, so before going to the okay, let me give the then it will be clear example. Let me first give me the example, then it will be clear. So example is these values are observed. So example 0 1 2 3 4 5. This is values, this is frequency. So the following the following supposedly 50 values generated from, these values are generated from, okay, let me give 11, this is 17, 10, 9, 2 1. So the given data are generated from Poisson distribution with mean 1 from computer programming. Okay, now let's check the hypothesis, null hypothesis H0, that is F0, that is the random variable of interest is Poisson with mean 1. So to do that, let's make a table. How do you, so first of all, the how many null observation is there, what is the probability, actual probability according to a Poisson distribution. Let's check it. That will be, so it should be lambda to the power n e to the power minus lambda by n factorial. So put n equal to 0, so e to the power minus lambda, that is e to the power minus 1, so 0.367879, what will be 1, that will be same 0.367879, what will be 2, that is 0.183940, what will be 3, that is 0.061313, the 4 is 0.15328, the 5th is 0.003066. And what will be then NPI, the expected value, this this, suppose this is K, this is not N, this is K. Okay, so how many observed values there? The 50. If we add those things, so we will get 50. So 50 observations are there. So if we multiply this probability with 50, you will get 18.394. This is again same 18.394, 9.1970, this is 3.0657, this is 0.7664, this is 0.1533. and you see the last 3 observations are very small, so let's put it together. So let's write it in PI. So 18.3940, 18.3940, 9.1970, this will be 3.9654. now what are the observed value y? So in 0 this is 11, in second this is 17, in third second that is 10, and the combined these 3, this is 12. Now what will be then n pi minus y its square by npi, that will be first 2.9722, this is 0.1056, 0.0701, one is 610.2795. so what will be the summation of this? Summation of this will be, so our chi-square will be, so this is the table. Now the summation of that means chi-square will be 9.427. now the upper 5% value of the chi-square distribution with k minus 1 equal to 3 degrees of freedom is chi-square 3, 0.05 is 7.185. you see this chi-square is actually greater than, chi-square is 19 and it is 7.815, chi-square is greater than 0.05. so from these data points we actually reject H0, and this is that. So from the chi-square test and from these observations we will not say that if I actually guess that although you see one thing, although these are generated from a computer simulated Poisson process with mean 1, we have to reject the hypothesis. So it says that this observation, from this observation, it is not there is enough evidence that we can reject our null hypothesis that these data are coming from a Poisson with mean 1. So that's it. Now we will see that what will happen, that if some parameters, okay, if some parameters of the distribution are unknown. So that we'll see now. So if some parameters are unknown, then what we will do, suppose then what we will do, then first we will estimate those parameters will first estimate those parameters from the observations. First we'll do that, this thing first we'll do. In the second, since we know the parametric form of the in which family, or we know that from which family these random variable are from, then we'll put those. So first of all, we estimate the parameter vector theta cap excuse me. Then what we'll do, then we will put these parameters in the distributions, put those parameters in this distribution, and from here we will find the probabilities that what is the probability that observation will belong to the ith interval. Now according this we will get the similar statistic I equal to 1 to k y minus n pi cap by n pi cap. Now one should focus in that thing, that here we use one for estimate this parameter. So the distribution of this chi1 square no longer remain a chi square with degrees of freedom k minus 1. Suppose we know the p numbers of parameters are unknown. So the p numbers of parameters were unknown. If the p numbers of parameter are unknown, then this distribution will be approximate, this distribution k1 square will be approximately chi square distribution with n minus p minus 1 degrees of freedom. These degrees and why the reduction of these degrees of freedom? Because we have already used our observed value to determine or to estimate the p numbers of parameters. So that's why we have to lose the extra degrees of freedom. So this is now another thing is that so this is if we estimate using, so okay, so this will be the case, this will be the case, this will be this case when we estimate the parameters by its minimum chi-square, minimum chi-square estimation. So this is the case when we'll estimate it by minimum chi-square case. Now Pearson has showed that if we Pearson has showed that if estimators obtained by the more efficient maximum likelihood method of estimation, then the asymptotic distribution is that chi-square now will be chi-square n minus p minus 1 plus z square, where z square equal to summation of I equal to 1 to p lambda I x square xi square, where xi's are independent, that means xi's, all xi's are IID, these also are IID taken from a normal 0 1 and lambda as numbers between 0 to 1. So now you see that if I estimate from the maximum likelihood estimated, then our actual the asymptotic distribution of t, so if I estimated through it maximum likelihood estimated, since you know that square of a normal standard variable is a chi-square with degrees of freedom 1, and from the linear property of the chi-square distribution we know that p the p IID chi-square will be, if a sum of the p IID chi-square will be again a chi-square with degrees of freedom p. So that means if I estimate through maximum likelihood estimator, then my actual test statistics will be stochastically, that means chi-square is stochastically bound between chi-square k minus 1 and chi-square k minus p minus 1 variable k minus p minus 1 random variables. Now these, if I in this situation, the critical points in this situation, the critical points from chi-square k minus 1 distributions will lead to a conservative test, and from these chi-square k minus p minus 1 will lead to anti-conservative test. And here our also test is same, that if it is greater than this, will be say will reject the null hypothesis. So let's see an example. Okay, let's see an example, then we will end this session. Okay, example of this. So the data is taken from a handbook of small data set. Okay, so this is not important. Okay, this is not very important thing, so let me give the example. So the number of cycles to failure of 22 ball bearings are given. The data is already in the ordered form. So the data are 7.88, 28.92, 33.00, 41.52, 42.12, 45.60, 48.48, 51.84, 51.96, 54.12, 55.56, 67.40, 68.64, 68.88, 84.12, 93.12, 98.64, 105.12, 105.84, 127.92, 128.04, 173.40. Here aim is to test H0 is f0 x equal to 1 minus h0 minus lambda x, where x greater than 0, lambda greater than 0, and we don't know this mean with mean 1 by lambda, which is unknown, so the maximum likelihood estimator of lambda is lambda cap is n by summation of observation sum, so that is here 72.3873, so that is equal to 0.0138. Now if I partition, okay, let's make it the table here. So partition n p cap y, and this is this. Okay, so this is partition. So by what is the number between 0 to 40, observation between 0 to 40, 40 to 80, 80 to 120, 120 to 160, and 160 to 200. So this is what is the partition. Okay, let me write it. Partition. This is pi cap. This is in pi cap. We estimated this lambda, and with using lambda here we will calculate the probability of being in the interval between 0 to 40. So we basically integrate from 0 to 40 this distribution function by putting lambda is this, and we will get some numbers. What will be the number? First number is 0.42. Will only second digit, up to second digit will write it 24. This will be 0.14. This will be 0.08, and that is 0.04. and what will be np cap? What is the n here? So total observation, how much observation is there? 21 observation is there. If we multiply it by 21, you will get 9.33. this you will get 5.37, 3.02, 1.77, and you will get 1.02. so this is observed number. It is here 3, this is 11, this is 5 to 1, and what is the n? Pi cap minus y its square by n pi cap, that is 4.30, 5.88, 1.17, 0.02, and this is 0.00. so this is 0.03057, and what is the chi-square? That is 11.3946. so you see that with chi-square, with conservative test, that means with degrees of freedom only n minus 1, that is here 20. Here how many is there? 1 2 3 4 5. so chi-square 1 is 5. So chi-square should be is stochastically bound between chi-square 4 and chi-square. How many parameter we have estimated? Only one. So chi-square n minus p minus 1, so that is here 4, that is 3. So basically 5 minus 1 is 4 and 5 minus 1 minus 1 is 3. So that's chi-square 4 and 3. And we know that chi-square 4 0.05 is 9.488 and chi-square 3 0.05 is 7.815, and our observed number is larger than chi-square 4 with significance level 0.05 and 0.05. So the null hypothesis, null hypothesis is rejected using both the conservative and anti-conservative critical points. Now one thing is that if the observed number is remain between these critical and the anti-critical region, then we will that conservative and anti-conservative procedure, then we will always use the conservative procedure. So let me write it. If observed value happens to be between the conservative and anti-conservative procedure, we will use conservative procedure to reject the null hypothesis. So that's all for today's lecture, and tomorrow we'll see the one sample problem, how to check the one sample problem with which is actually known Wilson-Coxen test. So we'll see the Wilson-Coxen for one sample and two sample, and that's it for today. So thank you.